Hey everyone, welcome back to our channel. I am Somodipal and today I am going to present a very interesting and unique feature of our software PravahaSim, which you may not have seen before in any power system network simulation software. So we are going to show you the system frequency dynamics of hydrogen energy storage system or battery energy storage system integrated highly renewable penetrate power system networks in different scenarios. To demonstrate this, we came to our PravahaSim app. Now to show you this feature, I am loading a 9-watt system which is saved in my system. Now I am loading the 9-watt system from my computer. So here is the 9-watt system which I already made in my software. Here you can see in bus 3 a wind farm is connected in the bus 3 and wind farm designing is already done. In my previous video I already showed how to design the wind farm and inject the calculated power into the main software grid. Now we can see in the bus number 3 where the wind farm is connected, there the hydrogen storage system is also connected. But why it is connected and what is the need to connect it, I am explaining now. We all know that wind generators are converter interfaced, so they are not able to sense any faults happening in the systems and also not able to initiate recovery automatically as they have no natural inertia. So to do the recovery we need some manual or predefined control logic. After that wind farm can able to recover the fault and get back to the normal operating condition. But this control logic takes little bit time to actuate, during which the system frequency dips very much higher than the conventional synchronous generator connected systems. As synchronous generators have their natural inertia control which resists the rock-off and resists the frequency dip, as in high unit penetrated systems. This high frequency dip can cause grid failure or other vulnerabilities. So to resist the frequency drop, some backup system must be present to arrest the high rock-off during this fault condition, where wind farms take time to initiate recovery. For that purpose, defined energy storage systems are very much useful. In this video, I will show you the coordinated operation of two energy storage systems with wind farms separately. One is hydrogen storage and another is battery storage. Now come to simulation. Here you can see the hydrogen energy storage is connected in coordination with wind farm. Now if I simulate the fault induced frequency stability analysis, which I demonstrated in my previous videos, then you will able to see the difference of frequency stability between energy storage system connected and energy storage system not connected systems. For that I have to first simulate a fault. Suppose I am simulating the double LG fault, then running the software. Here you can see the double LG fault outputs are shown. After that I am opening the code editor using which I am going to show the fault induced frequency stability analysis. Now my code editor is open. Now this is the inbuilt code editor of our software. Here you can see some inbuilt logics are written, but you can change those logics to create different scenarios manually. For that, here you can see the manual hydrogen fuel cell parameters are selected as no. If you select it to yes, then you can able to change the hydrogen energy storage system related parameters. So here is the hydrogen storage related parameters are given. This is the actuation time of the hydrogen fuel cell, and this is the hydrogen capacity. Here fuel cell actuation time is written as 150 millisecond. Means after 150 millisecond the hydrogen fuel cell will start its working, and this is the capacity, means 90% hydrogen is available in the hydrogen storage tank. Now if I simulate this, one graph will show. Before that I want to show you a graph without any energy storage system connected. That is our previous fault induced frequency stability without any energy storage system connected. For that I am changing here the energy storage system support. It is written as with, means energy storage system is supported, means support is available, but it is I am changing it is from with to without. If I change to without, then after executing you can see this is the old graph where no energy storage system is connected. Here you can say a initial spike is there and followed by large frequency dip, and then later it rebounds when the wind farm takes the control and started its manual or predefined control logic. Here you can see a small spike is there due to inertial control mechanical power and electrical power disbalance during fault. But after that, if I change it from without to with, means energy storage system is available, that is our hydrogen storage system is available. So after that, if I click on execute, then you can see the small spike you have shown the small spike. Now you can see that the small spike I have shown you is this spike. It is showing as a large because now the frequency dip is reduced, and near about the small spike size, means after dipping the frequency to a little bit, the hydrogen storage system support the grid and frequency rebounds, and that's why the small frequency dip is observed near about the spike size frequency dip. You can able to relate from this curve. Now if I reduce the hydrogen fuel cell actuation time from 150 milliseconds, suppose I change it to 70 milliseconds, then you can see, if I click on execute again, here you can see this is the spike time only. Here near about this region, you can able to see the hydrogen fuel cell is actuated, and it takes the control. So the spike generally reduces, and after that no frequency dips observed because hydrogen fuel cell already supported the dip. This is one condition, and another condition you can see that when the hydrogen fuel cell actuation time is more, and also the hydrogen capacity is very much less. Suppose 5% hydrogen is remaining in the storage, then what will happen? Then suppose 3% hydrogen is remaining, then what will happen? Here you can see that after the initial condition, when the fault occurs, a small spike is shown. After that, hydrogen fuel cell start after small frequency dip, hydrogen fuel cell start its work and support the grid and frequency dip removed, and sustained power supply is there. But after some time, when the wind farm is not in control, at that time hydrogen is supporting the grid, but now its limit is reached, means hydrogen is emptied in the hydrogen tank. So no hydrogen remaining, means no power support is there, and wind farm also not in control. So there is lack of power. Due to this, again frequency dip is observed, and at this region the wind farm starts its control logic and able to support the grid and recover the frequency gradually. This is another scenario. Now you see 4 scenarios are there, among which one is the without energy storage system, another one is the with energy storage system but with different actuation time and different capacity remaining. After that, I am loading second system where battery energy storage is connected. Here I am loading on another system from my computer. Here you can see if instead of hydrogen storage system, on another battery energy storage system is connected. Now after that, I am doing the same thing, doing the LG fault only, and after click on run simulation, I am clicking on the code editor button. Here you can see some predefined control register written, and manual battery energy storage parameter control is selected as no, but I am selecting it as yes to do the to change the manually parameters. Here you have to change those parameters: battery actuation time 100 millisecond and battery capacity 70% remaining. So after that, I am showing you the graph without battery energy storage system connected. So without, I am selecting without and executing the curve. Here you can see small spike like previous, and followed by a very big frequency dip, and then later rebounds. Now if I change it from without to with, and battery activation time as 150 millisecond like the hydrogen storage, you and execute it, you can see a similar type of graph. Here the small spike is shown as much big because frequency dip is very much low, so, compared to the spike. So you can see after small frequency dip, frequency rebounds. Now if I change the actuation time from 150 to 50 milliseconds, suppose, if I select it, then here you can see the graph after some spike here approx here the battery storage system start activating, means it is in charging state, because in spike during spike what happened, the electrical power reduces, means the load power reduces, but mechanical power not able to reduce that much quick of the surrounding synchronous generators. So they supplied power, but there is no one to consume that power, so initial frequency is spike is observed. But as there is a fault, so the system frequency system is not able to supply the power to the grid, so later a deep huge frequency dip is observed, as most of the systems are wind turbines, and they have not any natural inertia, so they are not able to supply the power or change its inertia. So, that's why the large frequency dip is observed after that. So during the spike time, if the battery energy storage system or hydro energy storage system activated, then what happened? It will consume the extra power generated and reduces the spike. And after that, when it enters the frequency dip region, then as already the energy storage system is actuated, so it started supplying the system and no frequency dip is observed. Now if I change the actuating time from again 50 to 150 milliseconds, but change the battery capacity from 70% to 20.5%, because I'm selecting at 20.5%, because battery to maintain the good health of the battery energy storage, means like lithium ion or any type of batteries which is able working here, the battery is not fully charged, not fully discharged in every life cycle, means the logic is like that battery energy storage system cannot be discharged below 20% and cannot be charged above 95%. To maintain the battery health, this logic is made. Now if I do the battery capacity as 20.5%, means 20% is a power which I cannot use, means only 0.5% battery is remaining which is usable. Now in this condition, if I click on executor go, then you can see a curve where after initial small spike, initial small frequency dip is observed. Then after that battery energy storage start actuating its control and recover the frequency, but after that after applying the power up to certain time, its remaining capacity ended, means the 0.5% charges SOC is decreased and it's hits the minimum limit of 20%. So battery logic stop the battery power supply, and at that time as wind turbines or wind farm is not in control, full control, so they are not able to supply the grid entirely, and so the grid frequency again start decreasing, and at that this portion wind farm take the overall control and support the grid entirely and recover the frequency gradually. So this is the fourth piece, like the hydrogen energy storage system. So these are the two hydrogen energy and battery energy storage system integration related things. Now I want to show you another feature of my software, which is the bulk wind data processor. Means suppose here the wind farm is connected. For that I am selecting another model. Suppose I am selecting this model. Here you can see one only wind farm is connected. Now if I without energy storage system, if wind farm is supporting the grid with its power, then what happened, as wind farm is related to the wind speed, means if the wind speed is high, then wind farm can produce more power, and if wind speed is low, then wind farm can not able to produce the required power as required, it produces less power. And also the wake effect also reduces the power, so wake effect is also very crucial parameter. So after that, after calculating wake effect and watching the wind speed, if wind farm not able to supply the required power, means if load and generation mismatch is there, then supply system frequency may be not stable. So to check that, I am doing this simulation, that is bulk wind data processor, where you can able to see up for a certain period like 1 day or for 1 month, and in a time gap means for 10 minutes for 1 hour, like that you can able to check the wind speed and according the system frequency due to the variation of the wind speed you can able to see. For that I am clicking on the wind farm icon, and here you can see a open wind farm batch processor option is here. If you click on that, another sub window is open. Here you can see the wind turbine parameters can be settled like row, column, X spacing, Y spacing. Different type of wind turbine models are given. Here one option is there, upload Excel or CSV file, using which you can able to select the series data. Means for now I am selecting one data set, that is 1 day data of 10 minutes interval, means total 144 data sets you can found. For that I am opening the data, and you can see here the data is fetched. Now I have to rearrange the data as per the requirements. Now wind speed, wind direction is settled. Now I have to select the model. I am selecting the VESS V90 3 megawatt model, and leave the remaining as same. Now after that, if I click on process or rows, here you can see the row process 144 rows, as I already mentioned, 144 total rows are there. Now if I show you what is the scenario now, here 144 rows are calculated. Here you can see 144 up to 144 it is showing. Now wind speed and wind direction is given value, means inputted values, and based on the wind direction the angles are calculated. Now from those inputs, this total wind farm power is calculated, where 3x3 row column is there, means 9 wind turbines is there, and based on the wind speed and wind angle, after calculating the wake effect, what is the total wind farm power, means the total power of all the wind turbines produces, it is given here, shown here. Here you can see due to wind speed and wind direction variation, the wind farm power also varied. But now if I inject all those wind turbine total powers in my software, main software PravahaSim, then what will happen? It will check one by one, by putting one by one wind farm values in the main grid, and checking the it will check the total grid frequency. Now if I click on the inject to main app, means inject those wind farm values to the main app, then what will happen? You can see. After that, here is a prompt is given to select the reactive power. I am forgot to select the reactive power before, so I have to select it now. I am giving the 0.01 as a reactive power value. Now you can check it is working in the background. Actually, here you can see the wind farm is working, and here the graph is shown dynamically, means here you can able to see the 144 values are shown in this graph. This green color cycles are 1 frequency, means total 144 frequency throughout a day in 10 minutes interval, after putting all the powers in this PravahaSim model, 9 bus model. So here you can see the frequency varies very much due to this wind speed variation. But if I connect the hydro energy or battery energy storage in the main system, then how this frequency can be supported in normal operating conditions also, so that sustained frequency of near about 50 Hz is available throughout the time. Means if frequency dips, then it will support the grid by injecting more power, and if the frequency is more, means power is more than the load demand, then it will absorb the power and produces hydrogen if the hydrogen storage system is connected, and it can be charged if the battery energy storage system is connected. Then how it will do it short, I will show you. For that I made another sub software, that is Urja. Here I will show you that. Here, this is the Urja app. where three processors are given. That first one is wind farm power processor, second one is hydrogen fuel cell and electrolyzer system based frequency processor, third one is battery energy storage system based frequency processor. In first one, here the buttons are there using which you can able to toggle between the windows. In first window you can see, after clicking on the button, you can see in the first window what I already shown you, that is with only wind farm connected system. By this I already shown you, so I am not going to show you this again. Now this is the wind farm connected system with hydrogen energy storage system is there. So now this one is the hydrogen system based frequency processor, where with wind farm the hydrogen energy storage system is also connected in the 9-bus system, or in the system which you can able to simulate in PravahaSim software. To simulate this scenario with hydrogen energy storage system integrated, we have to again upload the file where the all data are there. Means I am selecting the same data, means 1 day data of 10 minutes interval, means total 144 data sets. I am rearranging the system. Now if I select the wind turbine model, same wind turbine model is selected, and row columns are also same as previous. Now here you can able to change some parameters related to hydrogen energy storage system, like electrolyzer efficiency, fuel cell efficiency, storage capacity, initial storage. Here the nominal frequency you can able to set, that is set to 50 Hz by default, as our grid is work at 50 Hz. Here the P committed value of hydrogen storage system, P load means load power requirements, everything is there. After that, if I process all the rows, here you can able to see 144 rows are processed. Now here you can see, based on these inputs, wind speed, direction, the total wind farm power is selected, and based on this P load and P committed values, the total power requirement is calculated, and also based on this how much hydrogen storage is available, and among this, if hydrogen is produced due to high frequency, or if the hydrogen is supplied to support the grid using injecting the frequency, that also can be shown here. If the hydrogen production is 0, means no hydrogen is produced, means frequency is below the system frequency, so hydrogen fuel cell have to support the grid by injecting power. So for that, fuel cell is acting. Here you can see 50 frequency is near 50 Hz, means 49.9 Hz. Now here, after some time, when the hydrogen fuel cell storage get emptied, means no hydrogen is remaining in the storage, then hydrogen storage go to 0, hydrogen production is also null, and hydrogen fuel cell power go to 0. And at that time you can able to see from 49.9 Hz it is decreasing to 49.8 like that. But after some time, when excess power is available from the wind farm, then after giving the power to the load, how much power is available, that much power is headed to the hydrogen storage system to produce hydrogen. Here you can see hydrogen storage is increasing slightly, and hydrogen production rate is also there, and fuel cell, no hydrogen support is needed, so fuel cell power is 0. And now frequency is increasing from 49.88 to 49.9. Here you can see, after some time, again the same condition is there. When wind farm power is less, then hydrogen have to support the grid, and after some time charging, discharging, means like hydrogen production and hydrogen supply both are coordinately doing. Now I am able to plot a frequency curve. I can able to plot a frequency curve like the previous one, where by using the generate frequency plot this button. Here you can see in previous curve, where no energy storage system is connected, at that time the frequency curve is very much fluctuating, where you can see the frequency sometimes very much decreases, sometimes very much increases. Due to the variable wind speed, the wind farm power is also variable, so system frequency gets varied. But now, as the hydrogen storage system is connected, it can supply power, or when the excess power is available, it can absorb power to make the hydrogen, produce hydrogen in the hydrogen storage tank. So the system frequency gets nearly stable, means nearly 50 hertz supply. You can see where nearly straight line is shown, where nearly 50 hertz frequency is maintained throughout the day with energy storage system integrated. Now if I do this same simulation with battery energy storage system, for that I have to click on this button. This is the battery storage system based tab, and I have to do the same thing. I have to select the 10 get data of 1 day. Now I have to arrange the data, and after that I am selecting the same wind turbine model, and here after selecting the row column, you have some more options are there related to battery. That is the battery storage capacity 100%, peak, how much power is committed for supply, and SOC value is means the how much charge is available in battery. 70% charge is available here. As I shown you that SOC minimum and SOC maximum values are there. Based on this, here the SOC min and SOC max are given, means below 20% battery cannot be discharged, and maximum 85% battery can be charged. Here you can able to change the values. I am selecting it 90%, 95%, means up to 95% battery can be charged, means to maintain the battery health for a longer time. And here also nominal frequency is settled to selected as 50 hertz. P load is given. DT values means time interval during which the battery SOC can be evaluated, means after every 10 minutes the battery SOC is checked, which is in synchronism with the my inputted data, like the 1 day data of 10 minutes interval. So like that. Now if I click on the process or rows, here you can see 144 data are processed. Here sometimes SOC is primary SOC you see in here the 70% SOC is available. Now as the battery is supplying power, as wind farm power is less than the load power, so SOC is supplying the power, so battery is supplying the power, so SOC decreasing from 69 to 68, 67, 66 like that, and frequency is maintained in a constant like a constant value. But after some time up to this it supplying the frequency, so the SOC is decreasing from 70% to near about 28%, 29%. But after that, when the wind farm power is higher than the load power, then wind farm can able to charge the battery also. After supplying the load, the remaining power can be fed to battery to charge the battery. So from 29% SOC is increasing to 30.06%, means battery is charging, not discharging. So DOD also reduces from 70% DOD, means depth of discharge to 69% depth of discharge, and frequency also improved from 49 hertz to 50 hertz. Now like that, charging discharging is available throughout the day based on the wind speed and wind farm power available. And now if I click on the generate frequency curve, you can able to see the throughout day frequency plots. Here you can able to see frequency plots are there, and based on this frequency plot you can able to see based on the battery supply and wind speed available in the wind farm and wind farm power production, battery is working, and nearly constant power like is supplied to the grid, so nearly constant frequency is also available throughout the day, like the hardware storage system connected. Here you can see the single type of nearly linear 50 Hz graph is shown throughout the day. So these all are the features that is very much unique and maybe not available in other power system based simulation software. And now after briefing all new and unique features of our software PravahaSim, I can say that the energy storage system integration in a power system network is very much required for smooth and stable grid operations in highly wind penetrated systems. So this is a unique and very crucial analysis feature and a new software for modern renewable grids in our main software PravahaSim. We hope this feature will help the users in their different analysis. We firmly believe that our Swadesi software will be a competitive alternative to the commercially available foreign software packages. It will help engineers, industry and academia immensely. For more details and download, visit our website www.pravahasim.co.in. Thanks for watching.